Now we're going to discuss quotient rings. So just like you can quotient a group by a normal subgroup and get a new group, it turns out you're going to be able to quotient a ring by a two-sided ideal and get a new ring. Well, let S be a subring of R. Then since R is an abelian group with respect to addition, it follows that S is a normal subgroup with respect to addition. Why? Because every subgroup of an abelian group is normal. In particular, the set of cosets, R mod S, is an abelian group. With this is the addition operation. So note here the group operation is addition, so we write the cosets additively like this. So the coset representatives look like R plus S now, so that is a big change from when we were working with groups. But so you just add the representatives. One question we can ask is, when is this set of cosets a ring? So one thing we try is, how about just defining the product to consist of the product of the coset representatives? Well, we run into a well-definedness problem. This formula depends on which coset representative you picked. Notice I'm defining it in terms of R and R prime. But R doesn't define the coset. I could replace R1 with an R2 for any other R2 that's in the same coset, and these cosets are equal. Similarly, I could replace R1 prime with R2 prime for any other element in the coset, and these two cosets are equal. In order for this to be well defined, I have to guarantee that these two products belong to the same coset as well. If not, then it turns out I don't have a well-defined operation, because I could have more than one answer, and I want a unique answer. I want a unique product. So when is this actually well-defined? Well, we need this condition. When two of the first factors are equal and two of the right factors are equal, that the actual claimed product we want is also equal. Well, when is this true? Well, remember the definition, one of the equivalent definitions for equality of cosets would be when this quantity is true. Now here I will go ahead and remind ourselves that originally this is stated in this form. But here we are working with addition instead of multiplication. So you replace the times with plus, and you replace the inverse with negation, subtraction. And so that's what's going on. So this equality holds if and only if this difference is true. This difference is a little hard to work with, so the sneaky trick is to cleverly add and subtract R1, R2 prime. Why? Because in this first term you can factor out a common factor of R1, and in the second term you can factor out a common factor of R2 prime. And so we see, given two equal cosets and another pair of two equal cosets, we get a well-defined product if and only if this crazy expression is an element in our subring. Well, that seems like a lot to handle, so let's simplify things for right now. Let's get rid of this first factor, and let's just assume this second set is, these second two cosets are equal, and just simplify matters for a moment. So let's set R1 prime equal to R2 prime. This term becomes 0. This becomes 0, it doesn't matter. So then we're only focusing over here. And let's make our lives even easier. Let's set R2 equal to 0, so we're just looking at quite literally what happens when you're multiplying by the identity coset. that we want to make sure that's well defined. Because, if that's not well defined, there's no hope at all. So let's make our lives a little easier and set R2 equal to 0 as well. And why? Because then that becomes 0, and all we're left with is this crazy, ugly expression. Just becomes the statement that R1 times R2 prime is an S. And the only variables we have left are that we're just letting R2 prime be any element in R, and R1 has to be an element in S. Why? Because if R1 is not an element in S, this equality can't possibly hold. Where have we seen this expression? Oh yes, this is the definition of saying that S is an ideal, with a left ideal. You're saying if you multiply an element on S on the right by an element of R, you get an element of S. So we see if we want to be well defined, we need S to be a left ideal. Likewise, if we tell the same story on the other direction, if you set R1 equal to R2 to simplify matters and set R2 prime equal to 0, then what ends up happening? Well, if you set R1 equal to R2, this becomes 0, this term goes away. You set R2 prime equal to 0, this goes away, and you just get R1 times R1 prime. And we're just requiring that to be an element of S for all R1 prime in S and all R1 in R. So then you're saying S has to be a right ideal. So what we're getting from this is if multiplication operation we just created is well defined, then S has to be a two-sided ideal. Now I'm going to point out that that's actually what you need. So if S is a two-sided ideal, then this more ugly condition actually holds in general. So this attempt to simplify things to figure out what conditions we need on S was actually useful. And why is this useful? Well, because if S is a two-sided ideal and we have these two assumptions, then we know that R1 prime minus R2 prime is an element of S. And R1 minus R2 is an element in S. Why? Because that's the definition of equality of cosets. And since S is an ideal, then this product is also an element of S. This product is also an element in S. And since S is a subring, this sum is also an element in S. So we've satisfied this condition. And so by the previous calculation, that means these two cosets are equal. And so multiplication is actually well defined. So of course, if this is complicated, you could always read the book's attempt to prove it. I'm proving an if and only if, where the book only just goes one direction. So the books usually just say if you have an ideal, then the set of cosets forms a ring. I actually point out that you actually need the ideal condition in order to get the multiplication to be well defined. So it's actually an if and only if. If you don't have the ideal condition, then there is always going to be some case where the multiplication is not well defined at all. So then here's the theorem, the major theorem. Let I be a two-sided ideal of R, then R mod I is a ring. Here's the addition operation, and here's the multiplication operation. So now we're going to give the full proof. So R mod I is an abelian group under addition. Check. Why? Because R is a abelian group under addition, and I is a subgroup under addition, a normal subgroup under addition, and we've already proven that in that situation, R mod I is an abelian group with this operation. So we already got those axioms for free. We just need to do the rest of the proof. We just showed that multiplication is well defined, so I'm not going to check that again. So the only thing left to check are associativity and distributivity. So here's the proof of associativity. Take three cosets, multiply them together in order. By definition, the product of the first two cosets is the product of the first two coset representatives. Then the product of these two resulting cosets is Rs times T. But the ring is associative, so we can move the parentheses over. And then we can factor this triple product as a product of two cosets. And then we can factor this second product as a product of two cosets. And voila, we have associativity. Similarly, we have to prove the distributive property. These proofs tend to be a case of keeping track of the i's and watching them disappear. So we've got a coset times the sum of cosets. You add the two cosets together by adding their representatives. Then you multiply two cosets by multiplying their representatives. You can distribute the r over the sum. Then you can separate the sum as the sum of two cosets. And then you can factor each coset separately as a product of two cosets. And then it looks like you've got the distributive law. And you can check that you have the exact same identity on the other side. I include it because we're not assuming that the rings are commutative with respect to multiplication, so you do actually need to have the proof separately. So for the sake of completion, I have it. But you just copy and paste the previous proof and change what needs to be changed. So we do have associativity and distributivity, therefore R mod I is in fact a ring. So here's going to be my one and only example of a quotient ring. So my ring is going to be the polynomial ring with coefficients in z mod 2z. And my ideal is going to be the principal ideal generated by x cubed plus x plus 1. Note here, for space considerations, I don't write the plus I anymore, but here are the cosets. Well, I, 1 plus I, x plus 1 plus I, and so on. You notice there are no x cubed terms because in this polynomial, in this quotient ring, x cubed plus I is equal to x plus 1 plus I as cosets. Why? Because you have x cubed minus x minus 1, which is actually equal to x cubed plus x plus 1, because you're working mod 2, is an element of I. So you see that you only have up to degree 2 polynomials, and once you get degree 3, anything degree 3 or higher can be rewritten as a polynomial of lower degree. So even though this is a infinite set, this quotient actually ends up being a finite set with 8 elements. And so you can write down the addition. The addition table is actually not that hard to write down because basically it's just doing coefficient-wise addition, and 1 plus 1 is 0 mod 2. Which is exactly why you see this 0 down the diagonal, because when you add any polynomial to itself, all the coefficients become even. A lot harder is to write down the multiplication table. Okay, multiplying by 0 is easy, and multiplying by 1 is easy, but multiplying by the others gets a little harder. So when you're multiplying by low degree, it gets pretty easy, but as soon as you get, say, x times x squared, you get x cubed, and that's where that identity, the x cubed is equal to x plus 1 comes in. So I had to take that into account here. And similarly here, I got x cubed plus x. Or more accurately, from here on out, I started using the distributive law. I was multiplying x by a bunch of polynomials. I was just adding up entries from earlier in the table. So this was x cubed plus 1, so I was adding this entry plus this entry, and that gives me 1. X cubed plus x, I was adding, x squared plus x, I was adding this entry plus this entry. So you end up with this polynomial, and so on. So that was one way to do that one. And similarly for this row, I just add this row to this row. So there's easy ways to use the distributive properties of rings to simplify the calculations. And so then the only last row that I needed to do new calculations with was x squared up to here and here. And then I could fill in the rest of the table. So here was my table. So this is my quotient ring. And let's notice some properties of this quotient ring. So obviously you're going to get zeros, but I don't have any other zeros in the multiplication table. This tells me that there are no zero divisors, so this is in fact an integral domain. I see that the table is symmetric with respect to the xy axis, so this quotient ring is commutative. So yes, it is, and there is in fact a multiplicative identity, namely 1. So it is an integral domain. But something really curious happens. There's one appears exactly once in every row and column, every non-zero row and column. In other words, we actually have a field because we have multiplicative inverses. This is a field with 8 elements. So I once interviewed for a certain government job. The government agency shall remain nameless, and one of the interview questions in a live in-person interview working at a whiteboard was to give an example of a field with 8 elements. And so, I had to actually remember this construction, or at least a construction like this one, on the spot. And so this is a fact you can prove, and I was able to point it out, because of course he was trying to see. So a fact you learn very quickly is that Z mod HC is not a field because it has 0 divisors. It's not even an integral domain. But the more important fact is that for any prime power, there is a field of that order, of that size, surprisingly enough. They're all constructed, or the constructive way to prove that fact is exactly this approach. You take Z mod P, and you take the polynomial ring, and you find a polynomial of degree n. You take the principal ideal, and you take the quotient ring. The hard part is making sure you choose the right polynomial. Not every polynomial works. It has to be what's called irreducible. So it has to be a polynomial that doesn't factor at all over your coefficient ring into smaller degree polynomials. Of course, you have to wonder who cares, but in the world of cryptography and in computer science, P is often 2, because that's the way binary works. Fields of order 2 to the n are pretty important, so actually being able to construct them is actually very useful. And so there's an application of modern algebra to computer science. of course, it's an application of modern algebra 2. That's what the class you have to take in order to figure out and learn this construction.